All right, for sections 14.4 to 14.5, instead of just looking at the notes, we're going to actually go through several problems so you can kind of see how those notes apply to solving problems. And you can use these as examples. So we're going to calculate the pH of a 0.1 molar solution of HOCl. So the first thing to recognize is that this is a weak acid. And if it's a weak acid, you're going to treat it very differently from strong acids. So the first thing you want to do is to go ahead and list your major species. So you want to list the things that are in the solution, and we have two of them. We have HOCl and we have H2O. Of these two, the HOCl has a Ka value of 3.5 times 10 to the negative 8th, whereas water's is 1 times 10 to the negative 14th. So in this case, the HOCl is going to be a stronger acid than water, and so we're going to focus on HOCl. So we say that this one dominates. So even though water is going to produce a little bit of H plus and a little bit of hydroxide, it's not enough to change the pH compared to the amount that the HOCl is producing. So let's go ahead and write out our reaction. So we have the weak acid. We're going to pull off that hydrogen. And keep in mind that when you pull off the hydrogen, your new thing is going to go down 1 in charge. So since it was neutral, it's going to go down to -1. We can set up an icebox because this is a weak acid. Just as a reminder, you do not set these up for strong acids because we assume 100% dissociation. And we're actually mixing it with water as well, but this is a liquid, so we're going to ignore it. All right, so we can go ahead and plug in our initial concentration here. In the beginning, we don't have any of this because it hasn't broken apart yet, and we do have a very small amount of H plus from the water, but this is, so we'll put a little tilde there. That little squiggle means just a little bit, or very close to 0, but this is going to be insignificant amount from water. All right, we're going to shift it towards the zeros, so go ahead and add your x's. We don't have any coefficients. I should have added up here, so when you look at a question, you want to analyze the end of it first, what you're trying to figure out, and then kind of work backwards. And so since we're trying to calculate the pH, what we really want to know is the concentration of H plus once this weak acid has dissociated. So what we're trying to figure out is this X value right here, the equilibrium amount of H plus, because then we can take the negative log of that to get the pH. So now we have Ka and this is equal to the concentration of H plus times the concentration of OCl minus over the concentration of the acid. All of those are at equilibrium. We have x's for both of those. And we have this. Now we're going to go ahead and make the assumption that x is really, really small for two reasons. One is we're going to look at this exponent here and see that it's a really small Ka value. And if it's a small Ka value, that means that most of the acid is staying together. And so it's not going to change a whole lot. So that's one way we can do it. We're also going to go ahead and make the assumption that x is really small, and then we're going to go back and check and make sure that that assumption makes sense. So anytime you add or subtract a very small x, it's not going to change the amount that much. So 0.1 minus a very tiny amount is still about 0.1, and that will save us from doing a lot of the math. So we're going to go ahead and make that assumption. And we can solve for x. So multiply 0.1 times Ka, and then take the square root. Then what you want to do is just check that assumption just to make sure that it was okay to do that. And the way you do that is you put your x value over the initial concentration, or the initial amount, and then multiply it by 100, and it must be less than 5%. If x is less than 5% of the original concentration, then you can do that. So let's go ahead and plug that in. We had 5.9 times 10 to the negative 5th. For x, the initial concentration was 0.1 times 100 gives us a very small percentage. So we're allowed to use that assumption. And now that we have X, X is the concentration of H plus at equilibrium. So now we know that the concentration of H plus, once it reaches equilibrium, is going to be 5.9 times 10 to the negative fifth molarity. So to do the pH, we just take the negative log. And be careful with your sig figs. Make sure that you have those 2 decimals right there.